Alright, so today is going to be the first session that we talk about MIPS processors. You have a question? Oh, she did. Oh.
I was going to ask, so we shouldn't expect a quiz for this module right after? I'll ask you after this.
Yeah. Maybe, maybe not. I don't know. So MIPS processor module 6 is from chapter 4 of computer organization and design. Something that I want you guys to know is the quantitative analysis book by Hennessy and Patterson. It does have a lot of overlaps. So that's a misunderstanding that a lot of people think that the computer organization and design course is just for intro, and the quantitative analysis book is for computer architecture. These books have a lot of overlaps, and I personally like a lot of things that they covered in the computer organization and design. When you look at the quantitative analysis, almost 40% of that book is the chapters that they cover in the abstract. So when the computer architecture course is taught in many schools, top schools, they don't mention the equivalent chapter in the computer organization and design. Instead, they say Appendix B of quantitative analysis. But the reality is that the Appendix B of the quantitative analysis is, for example, chapter 4 of computer organization and design. Computer organization and design just provides more examples, and that's why I use that. Like, continue using it. These two books have a lot of overlaps. So if some of you heard this somewhere, that computer organization, this course is for this book is for the basic course, and then we have quantitative analysis. I don't believe in that, because these two books have more overlaps. And it's a very normal thing to cover appendixes in the quantitative analysis book. We don't do it here. Instead, we use the computer organization and design. Okay, so this is chapter 4 of that book. And we are going to cover basic MIPS processor implementation. A very basic one. And then we start from here, and we add different blocks to it moving forward. Okay? So what we're looking at here is a very basic view of MIPS implementation. It is designed for a subset of the MIPS instructions. Specifically, we're just focusing on load board, store board, and as memory instructions. Then we have AOV instructions, add, subtraction, and, or, set less than, and branch equal and jump. So the MIPS processor that we're focusing on now is just supporting these instructions. These are the blocks that we are somehow familiar with at this point. We got to know about the register file in module 3, and this was the block. It has different inputs and 2 outputs. And then we have the instruction memory. In module 4, we talked about how we go from an instruction that we see an assembly instruction to a machine code. And we mentioned that these machine codes are stored in an instruction memory. This is what we have here. We have an instruction memory, and this is where your machine code sits. In your project, you have 2 sections. You have a .text section and a .data section. So .data is where you use the data memory, and the .text is where the instructions sit. And the assembler is going to convert them to machine code, and those instructions are going to be stored in the instruction memory in forms of machine codes, 32-bit binary numbers. So these blocks we're familiar with, but now what we're going to do, we're going to cover every steps in the MIPS processor and see what blocks are activated for each step. So this is an abstract view, as I mentioned. The very first step for every instruction involves sending the program counter. So we know what the program counter is. Program counter is basically pointing to the address of the next instruction that we want to execute. So we read the register program counter, and PC register, and we send this as an address to the instruction memory, and then we read the instruction. This is called fetching. So we fetch the instruction, and we read one or two registers at the same time. So if it's a load word instruction, for example, in this case, this subset of the instructions architecture, if it's a load word, we read one register. If we have ALU operations, we read two registers. Okay, that's the very first step in every instruction. But looking at this simple abstract view, before jumping to the macro architecture and see what happens in every step, we need to know about an important block in the processor, which is called multiplexer. Okay. So as you can see in these points, these are some examples, but we have more of them in an actual processor. These points are the points that we have more than one input, but we just have one output. So for example, program counter can either come from this PC plus 4 or come from here. What we're doing here is calculate the branch target address, okay? But how we choose between these two possible inputs is through a multiplexer. We have another example here that is about the second input of the ALU. So the first input is always going from the register file, as you can see here. But the second input can come from either the instruction itself or from the registers. Okay? So, for example, if we have an immediate instruction, we have add I, which we are not covering in this subset, but if we have add immediate, the immediate part is directly coming from the instruction. And sign extended is 32 bits. And then we read one register. So we add a number with the register. This is always coming from the register file. The second part can come from the instruction or the ALU. So right here, we need to have a multiplexer to decide which path we want to take. So multiplexer has a very simple block. If you don't remember from digital circuit design course or digital logic design, we show it like this or this, it doesn't matter. But if we have, usually we have two N inputs and one output, and then we need N select lines to select each of these inputs. So for example, if we have a 2-to-1 multiplexer, like this, we just need one line to choose each of these inputs. So if it's 0, it's going to connect this path. If it's 1, it's going to connect the other path, the output. Now if we have 4 inputs with 2 lines, we can connect different paths. And I choose 0, 0, the first line is going to be connected, 0, 1, the next one, 1, 0, the next one, 1, 1, the next one. Okay. So multiplexer works this way. There are a bunch of switches inside the multiplexers. We have simple transmission gates, which are made by transistors, of course, and they just switch, they just connect the input to output based on the selection. So now if we add these multiplexers to the abstract view that we have, it's going to be something like this, right? So these points that we have to choose between the different inputs, we have a multiplexer, as you can see here. And now these multiplexers are controlled by control units. Okay, so we have different multiplexers, as you can see here. Besides multiplexers, we have different signals that we're going to talk about, like register write, and memory read. But some of these signals are coming from the control unit. Some of them are not just coming from the control unit, are also coming from the ALU. We have, if you remember, we had some flags, like a 0 flag and overflow flag. So we kind of talked about how we can use a 0 flag, but now the 0 flag is combined with another control signal to activate different paths. Okay? So this is how multiplexer work, and the control unit is there to choose the different path, activate different parts of the system based on the instruction that you want to execute. All right? if we're talking about the macro architecture, we need to provide some information about the MIPS. So I'm not sure if you remember, but we mentioned that MIPS is designed. In the very first session, we were talking about why we use MIPS in the scores. We mentioned that MIPS is designed in a simple way, and that's one of the reasons that we use it. The simplicity in MIPS enables us to use similar blocks for different instructions. Okay. For example, every instruction except jump uses ALU one way or another. It doesn't matter what the instruction is, I-type, R-type, load, store. Every instruction somehow uses ALU. So that makes it a little bit clear. You go from register 5, go from instruction memory to register 5, and then you know something is going to happen in ALU. Okay. So in case of the memory instructions, for example, we use ALU to calculate the addresses. You want to load something, you want to store something to the data memory, we have to calculate the address through adding the offset with the base register. So ALU is used to calculate the address that way. ALU instructions obviously use ALU. If we want to do add subtraction, that's clear. If we have a branch, we use ALU for a comparison. If you remember, the way the branch works is that we have branch equal, for example, T0, T1, and then jump to a label. Let's call it loop for now. So T0 and T1 are the two registers that we compare. And the way we compare it is through subtraction. And then we have the 0 flag, and we're going to use the 0 flag. We're going to cover that later in this module. So branches also use ALU. That makes it a little bit simple, because then you can plan for it ahead of time. So after using ALU, different things can happen. So in memory instructions, we have to access memory to either read something from the memory in the load word instruct case, or write something to the memory in case of store word. For the ALU and load instructions, we want to write something back to the register file. So if you have ALU instructions, you add to the registers, and you want to store results back to the register file again. If you're loading something, you go to the memory, you get the content from the memory and load it back to the register file. So this step is called write back. Now we have fetch, execution, and ALU. Some of the instructions might have a write back step too. Okay? In case of branches, we need to find where we want to jump to, and if we want to jump to that target. So we calculate the target address, and then we have a multiplexer that chooses from the next instruction and the branch target. Okay? So different things happen after using the ALU for the first time, depending on what the instruction is. Now let's build the data path. Okay, so let's go back a little bit. We mentioned that the first two steps, we send the PC to the instruction memory, we read the instruction, and at the same time we read either one or two registers. Okay, so in this step, these are the blocks that we need. We need a program counter register, we need an adder, because right there in the very first step that we fetch the instruction, we also increment PC by 4 because we want to point to the next instruction. That happens during fetching the first instruction. Okay. So this is different from ALU. It's just an adder that keeps adding the PC with 4. And then we have the instruction memory, which is where machine codes are stored. Okay. So these are the blocks that we need. If we put everything together, this is how the fetch step look like. Okay. So we have an instruction memory program counter where we don't care about what is happening before this. We have program counter going to the instruction memory. The output of the instruction memory is going to be a 32-bit machine code. We know how it is now. We're familiar with encoding and decoding. And then at the same time, we add PC with 4. Why 4? Because instruction memory is a byte addressable memory. Each instruction has 4 bytes. If we want to go to the next instruction, we actually need to add it with 4. Okay. So this is what is happening in the fetch step. Now, let's see what happens after that point. All right. So we start with the R-type instructions. In this subset of the instructions and articulation that we have is gonna be addition, subtraction, so on. So let's say we have an example of add T1, T2, and T3. So basically, we want to add T2 and T3 and put the result back in T1. This is how machine code looks like. Okay. So now the first step is we want to read two registers. Okay. Those two registers are T2 and T3. So we know the index number for T2. The index for T2 is 10. Okay. It means that in RS we have 0, 1, 0, 1, 0. Okay. This is the number 10. We send this number to the input, and T3 is the index number for T3 is 11. So it's 1, 0, 1, 0, 1, 1. This is what goes to the second register. Now we read the contents of those registers. The input is 5 bits, the output has 32 bits. Let's say the contents are 5 and 2. It's a 32-bit number, but we have a bunch of zeros here. 5 and 2. Now the next step is gonna be execution. So we do want to actually execute this instruction, which is add. We add these two numbers, we're gonna get 7. So we send these to the ALU. The output is gonna be 7. So this is what we get at the output side. And now we have the result of the ALU. Okay? So what's gonna happen here is the write back step. We have the result from the ALU, we want to write it back to the register. To write it back to the register, the first thing we need is where we want to store it. So we get register T1, the index for register T1 is 9. This is giving me the address to the register that I want to write the result back to. It's the write register. And now that I have the address, I can send the data back to the register file and it's stored there. Okay? But there's a little bit more detail involved here. So when we want to read the registers, you don't have to activate any signals. Okay? So that's because every instruction needs reading registers one way or another. Okay? So you don't have a signal, you don't have an activation pin that says, okay, read it. Okay? But for write operation, it's a different case. We have a control signal that tells us whether we want to write something back or not. Okay, so you have to set that signal every time that you want to write something back to the register, because it doesn't always happen. Sometimes we use ALU, but we don't want to write something back to the register file. Okay, so we don't activate write back signal. So for writing back, and that's why we have this register write signal here. Register write is activated, is set to 1 if we want to write something back to the register file. Okay, any questions? Is everything clear here?
So would the register write be just 1 bit?
Yes, it's just 1 bit. It's either 0 or 1. If it's 1, we want to write something back. If it's 0, we don't want to write anything back. Other questions? Good. So now that was an R-type instruction, like add. So what do we do for I-type instructions, like load board? Okay, so we have an example that is load board, register T1, offset T2. We know how it works. We get T2, we add it with offset. We go to the memory, we read something from the memory, and we write it to the register T1. Okay, so now for this, we need a data memory. So there's a data memory involved here, which is the .data part in your code when you store something to the data memory. And then we have a sign extension unit. We need the sign extension unit because my ALU is a 32-bit ALU, so it only accepts 32-bit inputs. Okay, so, but when you look at the instruction, machine code, the constant, which in this case is the offset that we use, is a 16-bit offset. So we need a block, intermediate block, that gets the 16-bit and changes it to a 32-bit number. Okay. Okay, this is called a sign extension unit. We know how sign extension work. We just designed a block for doing the sign extension. So these are the blocks that we need. Now let's see how it works step by step. So we want to read one register, in this case, write type instructions, and that one register is T2. So T2 has the index 10, or the 5-bit number of 01010. Okay, so as T2 is sent here, the content of T2 is going to the ALU, and at the same time, the offset is sent to the sign extension block. Okay, so 16-bit offset is going to the sign extension block to convert it to a 32-bit value. Okay, so now the 32-bit value goes back to the ALU. The first input is coming from the register, which is the content of address T2, address 10. And the second input of the ALU is coming from the sign extension block. Now we do the add operation. When it's done, we send the beta. This is the result. So this is how we calculate the address. We use the ALU to calculate the address that we want to store. We want to load something from. So now when we send the address to the memory, we can read the content from this one, read data. When we read data, we want to write it back. So what we do, we have the index for T1 going here as the address that we want to write back to. And this content of that memory block is going back to the right data. The T1 is used to address the right register. T2 and offset use ALU to calculate the address. When we have the address, we read the data, we read the contents of that block, that memory cell, and we send it back to the register file. Does that make sense? Okay. So now this is how load and store instructions work.
Shouldn't we like write it back to the data memory? Why would we go back to the register?
So this is load word, right? So load word is loading something from the memory and storing it to the register. If it was a store word, we calculate the address, we read the register, and then we write it to the data memory. But just because you asked that question, I remember that I forgot to mention something. So you see these signals here. We have ALU operation, in this case at 4 bits, for example, ALU operation. The 4-bit signal selects the kind of operation I want to do. It's add, subtraction, or whatever. Then we have a memory write and memory read, which is similar to the register write. So these two should be activated if I want to read something to them from the memory or write something to the memory. These are also 1-bit signals, and it's either 1 or 0, and defines whether we want to write something to the memory or not, or read something from it or not. Okay. So now if I put all these blocks together, this is what you can see here. I have an instruction. Forget about this part. We already talked about the fetch, which we had instruction memory and the PC, and the PC plus 4 calculated. This is what happens after that. We have instructions. The 16-bit part of the instruction goes to the sign extension unit, and then it goes to the multiplexer. Multiplexer chooses whether, let's show this. This multiplexer here, it chooses whether the second input of the ALU is coming from instruction, sign extended the instruction part, or it's coming from the register file. If it's an R-type instruction, it is coming from the register file. If it's an I-type instruction like load word and store word, it's coming from the instructions. It's going to be sign extended, the input goes here. Then we have an ALU source signal. The ALU source chooses between these two, which path we want to go. And then we have the ALU here and the data memory. And then we have another register, which is another multiplexer that chooses whether the thing that I want to write back to the register file is coming from the memory or is coming from the ALU. So if you follow this path, if the mem to reg signal is 0, the result of the ALU is going to be stored back to the register file. If the mem to reg is 1, the result of the value that we are reading from the memory is going to be stored back to the register file. Okay? We have two multiplexers. Just a question that you might just think about it. How do you think we decide what these signals should be? Because there is not a human being sitting there setting these signals. Right? What do we use to set this ALU source? Go.
Is it the function or the opcode?
That's right. So we have an opcode field and a function field, right? So based on the value of the opcode field and the function field, we decide what these signals should be. Okay? So we know, another thing I want to mention here is that if you have worked with application of specific integrated circuits, ASICs. Do you know what ASIC is? So it's a computing system. You can think of all of these different kind of hardware implementation that we have as computer systems. We have processors that we're familiar with. They are very flexible, but there's a lot of design, if you can say it, has been made in processors. There are a lot of things that we don't use when we're executing a program. We have FPGAs, which are a little bit more specific, and they're reprogrammable, but they're not CPU. They're specifically doing a very specific task. You can use FPGAs to implement a processor, but you can use them to implement anything else. And then we have application-specific integrated circuits, or ASICs. They're designed for a specific application, right? So when you design something for a specific application, you optimize it for that application, so you don't do extra things. CPU and processors are good for flexibility, but not necessarily in terms of the performance. So I can give you some examples here, and you can see why it is not very optimized. So this sign extension that I mentioned here, you can, for example, see that there's no signals here to control the sign extension. It means that no matter what, we sign extend the 16 bits of the machine code, no matter what. Even if we don't want to use it, we just sign extend it just in case. But there are a lot of blocks like this in processors that do some kind of computation which is never used. Okay, it's never used. It's used, but never used for that specific instruction, right? So there is a lot of over-design happening in processors just because of the flexibility. We don't have control over every single block in CPU. So in many cases, a lot of computations happen just in case it's going to be used. And then we have multiplexer here, choosing whether we want to use that or not. Right? Doing the sign extension, it means we are consuming power, we're consuming energy to do sign extension every single time. And then we have a multiplexer that might choose to use it or not. This is the case for processors. A lot of things happen at the same time, even if we don't really use them. Okay. We just design it in case it might be used for some instruction. Alright, so this is building the data path for load, store, I-type instructions, and R-type instructions. Now let's talk about the branch instructions a little bit. Okay, so as a reminder, we had this example in the instruction encoding module when we were talking about the branch. And if you remember, branch instructions use relative addressing, which means that in a case like this, we mentioned that when we want to find what this offset value should be, we go to the next instruction and count how many instructions we need to go forward or backward to get to the label, which in this case is exit. Okay, so now we have the relative number 2 here because when there is a branch, when we're at the PC plus 4, we need to move 2 instructions from that point to get to the address that we're looking for. Okay, so what it really means is that if I want to calculate the target address, I have to get this relative number and multiply it by 4. This is us adding 2 zeros, which is taking care of the multiply by 4. Yeah, multiply by 4. At this point, we know it already because 2 instructions, 4 bytes, and so on. So we multiply it by 4. We sign extended, as you can see here, and then we add it with PC plus 4. That's how we calculate the branch destination address. Okay. So this is calculated just in case, and we might not use it, or we might use it. Okay. On the other hand, we have PC plus 4 calculated all the time. So we have PC plus 4 here, and the branch destination address calculated. Both of them are going to a multiplexer. And then we have this multiplexer choosing between PC plus 4, which is the next instruction, or the branch destination address. But how we set this multiplexer is something that we want to cover now and see how we want to do it. Okay. So if we put together the block, what I just explained, we already have the PC plus 4 taken care of at the fetch step. So you're not seeing fetch somewhere here. The PC plus 4 is coming here. The 16-bit of the offset value is coming here. So if you look at this branch, there's a I-type instruction, and this offset, this constant value is in the 16-bit. The least significant 16 bits is sign extended, and is shifted left twice, or multiplied by 4, and then it's added by PC plus 4. So branch target is calculated here, and then we have the ALU that we use to compare two registers. Now, here we don't really need 2 shifts because we always know what we want to do. Shift has some extra operations, has some extra computation that define, okay, you have to make it flexible, but in this case we don't have to have a flexible shift, so we just concatenate 2 zeros. It's not really a shift because we always know what's going to happen. So we just put shift left 2 here. And then this block, so now this is where we use it. If you remember, we had a 0 flag in the ALU. I mentioned a few times when we want to do branch, we read 2 registers, let's say branch EQ, PEQ, T0, T1 loop. So we read 2 registers, T0 and T1, and then we need to do something about compare these 2. So we simply do a subtraction. If the result is 0, it means that they're equal. If the result is not 0, it means that they're not equal. But how do we know it? It's through the 0 flag. If the result is 0, the 0 flag is going to be set to 1. If the result is not 0, the 0 flag is 0. Okay. How does that happen? It's actually a very simple logic circuit. So you see you have the result of, so if you do addition or subtraction or whatever, you get this result, and then you have a NOR gate. Okay, so NOR gate, it means that if one of these bits is 0, if one of these inputs is 1, the output is going to be 0. It is enough to have one single 1 in all of these bits to have a non-zero result. So if one of these guys is 1, the output is going to be 0, and that's enough. If all of them is 0, the output of the NOR gate is going to be 1. So you simply use a NOR gate and connect the output of the ALU, every single bit in the output of the ALU to this NOR gate. And if the output, everything is 0, the output is going to be 1. Okay, that's how we create the 0 flag. Now let's see how it works. So we subtract RS RT, and then we get the result. This is the 0 flag. It's going to be set to 1 or 0, depending on the result of the subtraction. If the 0 flag is 1, we come here and we take the branch. This multiplexer is set by the 0 flag, and it decides whether we're going to go to the next instruction or we want to go to the branch target address. Okay? So if it's 1, we're going to choose this path. If it's 0, we're going to choose the other path. Okay? In reality, I don't think we have it here. We have this PC source. There's a little bit more details involved here. I had it in an earlier slide, so I go back so I can show it to you. But this PC source is a signal that decides whether we want to take the branch or we don't want to take the branch based on the output of the AOE. Let me see if I have it. If I don't have it, let's go back there and then we stop here. So this was the plot that I had in the very beginning. Okay. So there are two things happening here. I have a signal coming from the control unit, and then I have the output of the 0, and then this signal is a branch signal. If there's a branch instruction, the signal is going to be 1. If it's not a branch instruction, the signal is going to be 0. Then we AND these two signals, and then we send it to the multiplexer. To this PC source that we're showing in that slide is the result of ANDing branch and 0. Can you tell me why do I add this? Why don't I click and just directly connect 0 to the multiplexer here? Why do I add an extra AND gate and a control signal called branch instead of just directly connecting 0 to the multiplexer? As I explained, we can use 0. If 0 is 1, we take the target address. If 0 flag is 0, we just go to the next instruction. So we can use that, right? Go Xander.
Is it just because you don't want that 0 if it's in a non-branch instruction to accidentally change which PC counter it is?
That's exactly the reason, right? You might subtract two things and get 0, and you're not necessarily doing a branch. You're simply doing a subtraction, right? So if you just directly connect it to this part, every time that we get a 0, it just jump to another instruction. We want to make sure that this subtraction is done for the branch, not for subtracting two numbers. This 0 flag, this is again one of those other things. Every time this 0 flag does a computation and returns a 0. Even if I want to add two numbers, if the result is 0, the flag is going to be set to 1. Flag doesn't know that I'm doing a branch or add or whatever. It doesn't care. What it does, it doesn't care why I'm getting a 0 at the output of the ALU. It just sets the flag to 1. We are responsible for creating a mechanism to make sure that the 0 is created for a branch or it's not created for a branch. So this branch signal is another signal coming from the control unit. Control unit makes the decisions based on the opcode and function fields. Okay? That's it for today.